이제 첫 번째 연사를 모시겠는데요. 사실 키노트 스피치로 두 번째로 저희가 선정을 한 정말 중요한 분입니다. 이분은 MIT 미디어 랩스라는 정말 유명한 기관에서 리서치 사이언티스트로 활동하고 계시고요. Tadge Dryja라는 님께서 비들 아시아 2019의 1일차의 문을 열어주시겠습니다. 제목은 Utreexo Bitcoin for Nodes and Kilobytes, not Gigabytes라는 주제로 발표해 주시겠습니다. 큰 박수로 모시겠습니다.
Okay, hello everyone, good morning. So this is the first speech, not too many people, so not too much high pressure. I'm going to talk about Utreexo. So a little intro, hello, I'm Tadge Dryja. I work on Bitcoin at the MIT Digital Currency Initiative, which is one of the first university organizations that started supporting and developing these things. I've previously wrote the Lightning Network paper, a paper about discrete log contracts, smart contracts on Bitcoins, and today I'm going to talk about Utreexo. It's really cool being here and seeing like all the different things people are working on, although it is weird because it feels like I don't think there's anyone else working on Bitcoin that I've seen at this event, or really at any of the places I was yesterday. And so I was talking to people this morning, like, wait, this isn't like a niche thing, right? Bitcoin's like the biggest one and the first one. And so I sort of had to like, because I sort of feel like I'm in the minority sort of working on some weird niche little project here. But yeah, Bitcoin's pretty cool. So I'll talking about scalability. And scalability is one of the biggest issues, if not the biggest issue, in all of these systems. There's been enormous amounts of discussion. In fact, it's the first thing anyone ever said about Bitcoin. So November 2008, Satoshi Nakamoto, he writes online, he says, hey, I've been working on a new electronic cash system. It's fully peer-to-peer, no trusted third party. And the first response anyone that we know of responded on the internet and said, hey, we very, very much need such a system, but the way I understand your proposal, it does not seem to scale to the required size. And here we are, over 10 years later, we're still dealing with this. And the main thing he looked at is, you need to keep track of everything, right? Bitcoin is be your own bank. You've got to keep track of every balance or every UTXO, and that's hard. So what are we keeping track of? And so one thing I do want to say is, I hear a lot that proof of work is bad for scalability. And I really couldn't disagree more. Proof of work has its faults, certainly, but is amazing in terms of scalability. In Bitcoin today, we validate all the proof of work that Bitcoin network has ever done. It takes about 10 seconds. And we could reduce that to probably milliseconds, but we don't care because 10 seconds is minimal. So that's not even on this chart. But the main things that we have to deal with, they're pretty big. You've got the blocks, and you've got chain state. And if you go into your Bitcoin folder, if you're running it, du-h, see how much space things are taking up. The blocks folder right now is about 245 gigabytes, and chain state is about 3.5 gigabytes. Then what are these things? So a lot of people know, like, okay, blockchains, they don't have good scalability. The blockchain is really big. There's all these problems. But what are these exactly? So the 245 gigabytes, that's the blockchain. That's the history of all transactions that have ever happened since 2009. And we need to download that so that we can get to the current state of the system. That's the only way we know to do that other than sort of trusting someone. Well, that's not true. Like, there was talk yesterday about Mimblewimble, which has really interesting techniques that can in some way cryptographically skip through downloading and verifying all the state. But for Bitcoin, you download the 245 gigs to replay the last 10 years. And then the end result of this is this 3.5 gigabyte state. It's every UTXO, every coin that exists, what coins there are and who owns them, how big they are. And we need this in order to verify the next block. Because if we don't know what coins exist, if we see a block that spends coins, we don't know if it's actually spending something that exists or not. So the main problem is the UTXO set, right? So here with this 245 gigabyte blockchain, you can actually throw that away. And Bitcoin Core and other clients have been able to do that for years, 4 years now, I think. If you're running Bitcoin QT, you go into the little menus and settings, and you can just say, yeah, delete that whole 245 gig blockchain, and it works just fine. You still need to download it to get to the current state, but you don't need to keep it on your hard drive. So we've got that. That's cool. But you still need to keep this 3.5 gigabytes. And how do we reduce this? This is pretty heavy, and it needs to be pretty fast. So we can keep it from growing much bigger. Lightning Network certainly helps. SegWit tries to incentivize keeping the UTXO set size smaller. But ultimately, we need a pretty big UTXO set. If you want adoption and you want lots of different people to be using this, everyone sort of needs to at least hold their own single UTXO. Otherwise, they don't own Bitcoin, right? If you go to an account on an exchange, yeah, the exchange might only have a few dozen UTXOs for the entire exchange user base, but you don't really own that coin. So this new idea is called Utreexo. And a little explanation. UTXOs are outputs of transactions that have not yet been spent. And this is different from the account model that some coins use, like Ethereum, where in Ethereum it's a bit more intuitive than I have an account. The account has an address and it has a balance. So coins can come in and coins can go out. So if I have 10 coins and I send you 2, I'm left with 8. That seems reasonable. Bitcoin does not work that way. In Bitcoin, if you have 10 coins, you might have them in a single UTXO, or you might have them in several. If you have a single UTXO with 10 coins, and you want to send someone 2 coins, you send them 2, and then you send 8 to somewhere else that you control. You can't just leave 8 back in your UTXO. UTXOs are only spent in their entirety. Another thing that's confusing, especially if you look at web explorers, addresses don't have Bitcoin. Addresses don't have UTXOs. UTXOs have addresses. So you might have 3 UTXOs with the same address, but from the software's perspective, they're 3 distinct UTXOs. And while this seems like, oh, who cares, they all work the same, and that's sort of what I thought until I started working on this about a year ago. Now I'm like, oh, UTXO model is so much nicer. You can do so many cool things that are really harder. While the contract, like the account model is more intuitive, computer science-wise, I like this way. So UTXOs are pretty small. They're 64 bytes each. They have like a pub key script, the amount to show how many Bitcoins, and like the TXID. So they're tiny, but there's lots of them. There's about 60 million of them now. And it generally goes up. So in this chart, you can see, I think can't read at the bottom, but it's like 2014 to today. And generally, yeah, as more people are using Bitcoin, the Bitcoins get sort of spread out into smaller increments and more people are using it. It can go down, however. So you can see that sort of peak. That was like December 2017 when everyone was into Bitcoin and the price was skyrocketing. And then early 2018, it went down. And we don't really know. It's a decentralized system. But I think that was large exchanges generally consolidating their UTXO sets. So it can go down, but the general trend is up. Long term, the expansion of this UTXO set is a big concern in Bitcoin. It's one of the primary scalability concerns. Because while you can prune the old blocks and get rid of the blockchain data, if you can't store the UTXO set, you can't run a full node, and you can't verify things. So right now, yeah, it's only 3.5 gigabytes. That still can be fairly hard to run. It's also very disk I/O intensive. So if you're running on a hard drive, like a mechanical spinning hard drive, it's slow. Your CPU is sort of waiting for you to read these thousands of things every block. So if you can't store the UTXO set, you can't validate. Or can you? So that's where we're going with this. One initial idea that was in the original white paper is SPV, which is Simplified Payment Verification. So the SPV clients, which there's many of, they do not store the UTXO set. They just assume that blocks are valid because there's proof of work on them. This is risky, but in practice it's worked okay. You just say, well, I can't validate a signature. I have no idea if these coins are in existence, if there's the right number of coins. I don't know anything. But I see that this got into a block, and I see that this block has been confirmed 10 times. There's 10 blocks built on top of that. And I know that there's so many zeros in this hash function output that someone needed to work really hard to do this. So probably it's okay. And that does work, right? But it's risky, and not everyone can do it. And we know the attacks, right? We know how much these attacks cost. There's also a lot of privacy and other problems with SPV. So while SPV, I think, is definitely useful, I think we can do better. So the main thing that I've been working with is accumulators. So the idea is, wouldn't it be cool if we could not even store the UTXO set? We don't have a database at all, but people can then prove that their coins exist. We can do that. So it's really nice because right now, if you're an exchange and you have 1 million UTXOs and you don't manage this, now everyone has to store that on their hard drive. So you're sort of polluting the network by using up more than your fair share, or whatever that means. But in this model, it's, yeah, what if we don't store these at all? But then when people want to spend their coins, they prove that their coin exists. So now if you're an exchange and you have 1 million UTXOs, well, it's your responsibility to maintain all these proofs. Seems more in keeping with, like, seems fair. So the basic idea of an accumulator, you need to be able to add something, delete something, prove that something exists, and verify that proof. So a trivial accumulator that doesn't really count is just running a database on your hard drive, right? When you add stuff, you write it to your disk. When you delete stuff, you delete it off your disk. And then the prove and verify are trivial. You just show that it's there, and people verify that it's there on their drive. The whole point of the accumulator is that you make this thing a lot smaller. So there are some accumulators where you have a constant size amount of data, so no matter how many things you add, it stays the same size. In the case of Utreexo, it's not constant size, it's logarithmic size. So if you add 1 million things to this database, to this accumulator, it ends up, you need to store about 20 things. If you add 1 billion things, you need to store about 30 things. So it grows, but it's still really small. So even if you have 1 billion UTXOs and 1 billion people using Bitcoin, you only need to store about 30 hashes, a few hundred bytes, no big deal. A nice thing in this system is when you're verifying something, you're also deleting it. The only time you need to prove that a coin exists is when you're spending it. And when you're spending it, you delete it from the accumulator or the database. So this actually fits really nicely with how Bitcoin already works. And so I don't have time to explain all the cool details of how it actually works, but it basically uses Merkle trees. It doesn't use any super fancy mathematics like class groups of unknown order and RSA accumulators and things like that, which there are papers about, which are really cool. This is just hash functions. It's just sort of a forest of Merkle trees, and things can sort of swap around. And you only need to store the roots of these different Merkle trees. So given that you just need to store roots that are 32 bytes each, and you need to store maybe 20 of them, that's like 600 bytes. So you can run a full node, you keep 600 bytes, that's it. It's really nice. And this is a full node, right? So some people might think, well, it's sort of like an SPV node, but full node is in fully validating. You verify every transaction. No one can dupe you in any way. You're not storing all the data, so you can't necessarily provide it to other people who want to download it. But for your own purposes, you're verifying every payment in the system. So every transaction, though, in this model needs to prove that the coins it's spending exist. So this is not something that exists today in Bitcoin. In Bitcoin today, you make your transaction, you sign it, and you broadcast it. And people look that up on their database and say, oh, yep, this coin exists, and here's the key, and it's the right amount, and the signature's good, so the transaction's good. In this new model, you need to prove that your coins exist. Not just that you own them by giving a digital signature, but that they exist at all by giving a proof into the accumulator. And so this presents some problems. The first one is, how do I start using this? If I'm the first person using this software, I demand proofs for all my transactions. I say, hey, I'm using this new cool software written by people at the MIT DCI, it's Utreexo. I can run a full node, and it's really tiny. Now, everyone, give me proofs. And no one has any idea what this is. They're like, no, I'm running this software from a month ago. I can't give you a proof. I don't know what it is. So I'm stuck. And this is a problem. And the way we solve this is we have a bridge node. So the idea is a bridge node helps bridge the old and new networks. It's not trusted because you can't, a bridge node cannot provide a false proof, but it does have to exist and has to be able to prove everything that is in the current UTXO set. So this is actually very problematic for other constructions of accumulators where it's hard to update the proofs. So in Utreexo, the main design criteria was it's easy to update the proofs. It takes less than a second for a block. In other cases, it was very hard. So then the big downside, you need a bridge node, which is actually not too bad. You can run that on a laptop, and you only need one of them. You want more than one for fail-safe purposes. But a few bridge nodes scattered throughout the network would be fine. But then the big downside is now you need these proofs. So in addition to downloading blocks, you need to verify all these proofs, and those proofs are of significant size. So in the totally naive model, we say, okay, one proof for every UTXO being spent, maybe it's about 20 hashes. And then there's about 5,000 inputs in a block that you're going to have to prove. And that's like 3.2 megabytes. So this is a 4x increase in block size, retroactive. So all those old blocks from 5 years ago that are 1 megabyte in size, now they're 4 megabytes. So maybe some people would really like that because they like large blocks. But from a scalability point of view, this is actually not a good thing that you're going to have to download even more. So we need ways to cut that down. And there are quite a few. So I can go back. In these trees, I don't have a laser pointer, but you can imagine if I'm proving the leftmost two items there, I don't have to give Merkle proofs for both of them. If I give the two bottom left things, I only need to give one proof, right? Because they're sort of overlapping, the proofs overlap. And you get a lot of that, where a lot of recently added UTXOs get spent at the same time, and so the proofs get really small. You end up having, you prove like 10 things with one hash. So that's really nice. Another thing we can do is if we look at this is kind of a fun chart, a histogram of the lifespan of UTXOs. And it would be really interesting to see this on like different coins. So this is for Bitcoin, and it's data up to a few months ago is when I ran this. And the idea is on the y-axis, it's how many UTXOs, so it's a histogram. And on the x-axis is how long they lived, how long it was from the UTXO being created to the UTXO being spent. And so the largest is 10 to the 0, or 1 block. So UTXO gets created. In the next block, it gets spent. That's not the most popular. The most popular is 0, where the UTXO gets created and spent in the exact same block. So it essentially never touches the UTXO set. But I couldn't put that on the chart because it was bigger and doesn't work on a log scale chart. But you can see there's like a Pareto distribution where most UTXOs get spent really quickly. They don't live very long. They live less than a day, right? 10 blocks, that's an hour. No, hour and a half. I don't know. Yeah, hour and a half or something. So that 10 to the 1, that's 10 blocks. And that's like most of the UTXOs. They live so little. And then when you get to 100 blocks, you've got even more of it. What's also fun about this is the little bumps. So you can see there's a bump at 6 because people think you have to wait 6 confirmations. I don't know where that number comes from, really. There's also a bump at 433. I guess people like to wait exactly 3 days and then spend their coins. Who knows? But it's kind of a fun thing to like see all these weird patterns in the data. But we can use this to really improve the proofs for Utreexo. So naively, if you don't do any optimization, you're going to get about 600 gigabytes of proof to prove the 245 gigabytes of the blockchain. That's not good. But if you just aggregate within the block, it brings it down to about 240 gigabytes. So about 2x, right? You're downloading about the same amount of transaction data and proof data, which is, doable. It's not horrible, but we can do even better. You can remember the last 10 blocks, as I was showing this curve. Another thing you can do is ask the other nodes what the future holds. So when you're downloading the blockchain from someone, you're saying, hey, give me block 5, give me block 6, give me block 7. They know what happens next. Right? You don't, because you're on block 7, 8, 9. But they can sort of tell you, hey, this output doesn't get spent for 1,000 blocks, whereas this one does the next block. So they can give you little hints that really help your caching. So yeah, that really is very helpful as well. That brings things down even more. The servers can give hints about what transactions happen in the future from your point of view, because you're still catching up. So with that, we get this sort of main result. This was like most of the work, was getting this curve down. The more memory you have and the more RAM you use, the more you can cache and the less you have to download. And so you see on this chart, if you cache nothing, you say, nope, I'm going to use it in its pure form. I'm never going to remember anything. I have to download all the proofs. Well, then you're going to be downloading about 250 gigabytes. However, even a small amount of extra memory helps a lot. So if you say, oh, I'm going to I have like a gigabyte of RAM, which most people do. Now you get to that like 3K dot. And now you only have to download about 48 gigabytes of proof throughout the whole part. And that's pretty good. Like if you have to download the 250 gigabyte blockchain anyway, plus an extra, let's say 50 gigs of proof, that's 25% or whatever. Not too bad. And then I guess if you want to download nothing, you need about 12 gigabytes of RAM, which seems unreasonable because if you're going to do that, you might as well not use this at all. But the nice curve is the more memory you're assigning to this, the less proof you have to download. And for pretty reasonable amounts of RAM, like 500 gigabytes, 500 megs or a gig, which most computers have, the overhead for downloading these extra proofs is not too bad. So this seems pretty practical for regular desktop or laptop usage. Okay, so sort of getting toward the general idea here. This is pretty cool because it's not even a fork. It's not a soft fork. It's not a hard fork. Miners don't have to know. There might be people using this right now. Probably not because the software is pretty new. But you don't even have to know about it, right? People can just start making a bridge node. People can connect to those bridge nodes and start using this system to fully validate the Bitcoin network. So that's kind of fun. It's permissionless innovation. And I really like that because then I don't have to try to convince other programmers or other exchanges or anyone that this is a good idea. I just have to convince the people who want to use it. So then it also allows new cool things to be built. What do we build? So the obvious benefit, the obvious reason to do this is, okay, it's smaller, right? People don't run full nodes because they take up a lot of space, they take a lot of time. And so now you can say, hey, it's a kilobyte. You're good. Just run it. And that really helps. But there's a lot of other things that happen when your state is 1 kilobyte. So it's so small it can fit on a QR code. So maybe one thing you can do is you have a desktop at home. It's a pretty nice, powerful computer. You sync the Bitcoin blockchain, verify everything, and then you take out your phone and take a picture of a QR code and say, okay, now my phone is synced up. My phone, I trust my desktop, and my phone can take that state and transfer it just on a QR code. That is technically possible today. You could do that, download everything, and then transfer 3.5 gigabytes from your desktop to your phone. But it's big enough that no one does that. It's not really practical. Other things you can do is parallelize validation. So right now, when you're syncing up the blockchain, you download block 1, 2, 3. You have to go in order. You can't really check whether block 500 is correct before you've downloaded 499. Because block 500 is going to spend all these things that just got created in 499. However, with this, you could give out suggested states for a bunch of different blocks that are not trusted, but you can sort of optimistically say, well, this might be true. And if it is, I'm going to try validation among many different computers. And then at the end, see if it all links back up. So if you have 100 computers, you could download the blockchain 100 times faster. That's really cool. That's, traditional computer science scalability where, hey, I've got 100 times more machines, now I can go 100 times faster. So this is really another nice part of this system. There's other things you can do. So one of the big things is now if you have a spinning hard drive, you don't worry because you're never writing to disk. So the main problem now with speed for hard drives is you're going to have to read and write several thousand different UTXOs to your database, and that's going to take 10 seconds even. Because spinning hard drives, you got to move that needle back and forth a lot. SSDs are a lot faster, and so it's generally recommended if you're running a Bitcoin full node, use an SSD. For Ethereum, for example, you have to run with an SSD. With this, you don't care. Hard drive, SSD, it doesn't matter. You don't actually use it. It doesn't even stay in RAM. It stays in CPU cache because it's so small. So that's really cool. Okay, I think last slide. So generally, this is, okay, last slide, I'm wrapping up. The idea is now out there. There's a paper. There's code on GitHub. A lot of people ask, full nodes on phones? Maybe. I don't want to oversell it. You still have to verify everything, so there's a lot of CPU. You still use a lot of bandwidth. In fact, a bit more bandwidth than you would without using this. So if your phone can take it, the thing is battery is going to be bad. And people are going to be like, oh, I'm at 20% battery. This stupid Bitcoin, and then uninstall it or something. So I'm not sure that it's quite there for phones yet. But it's a really fun new research direction. There's lots of things to build, or BUIDL. And if people are interested in it, come ask, I'm around, ask me how it works, or tell me it doesn't work. If it doesn't work, I want to know as soon as possible so I can stop working on it. And there's code on GitHub. I'm trying to sort of make it cleaner and easier to read because a lot of this process was me trying things and seeing what worked and what didn't work, and it's changed a lot over the last 6 months when I've been working on it. So if you see it on GitHub, try to run it. If you see a problem, open a pull request or bug me about it. And I hope to work with a bunch of other people on it and hopefully get this into Bitcoin Core or other wallets within the next, 6 months, year. And hopefully it'll be a big thing that everyone uses. And also other coins, I think, can use it. Many different coins that are UTXO based. This is easy. It works the same. With account based, it might be a little more difficult. But there might be ways to get it to work in something like Ethereum. But it's harder because of the account-based system versus UTXO. Okay, so thanks a lot. And I guess no time for questions, but if you want questions, just come bug me later. Thanks.